So we've looked at finding the trigonometric function of an acute angle that is housed within the context of a right triangle. What happens though if we want to look at angles that cannot be written in a right triangle? Say for example you want to find the sine of 120 degrees. 120 degrees is not an angle that you can find in a right triangle. So we will extend the definition. And to do so, let's look at an angle that's in standard position. If we let AB be any point on the terminal side, and then R is the distance of that point to the origin, then one nice thing that we could do is we could drop a perpendicular line segment to the horizontal axis. And if we're dealing with an angle that lands in the first quadrant, then you can easily see a right triangle here. Now, then this is A, and this is B, and this is our angle theta. So therefore it makes sense to say sine of theta is B over R. Cosine of theta will be A over R. Tangent of theta is B over A. And then to make our reciprocal functions consistent with previous definitions, we have R over B, R over A, and A over B. And then we can go ahead and move this angle into different quadrants, as long as we maintain that A and B don't necessarily have to be lengths of sides. They are merely coordinates of an ordered pair on the terminal side. So let's take a look at an example. So let's go ahead and sketch our angle. So we have a point -3, 3. So that point is in the second quadrant. And we don't have to be too exact in our sketch of the angle. So there's our point, -3, 3. So let's go ahead and find R. R equals the square root of A squared plus B squared. So that will be the square root of the square of -3 plus 3 squared, which is the square root of 18, which is 3 square roots of 2. So if we want to think about this in terms of a right triangle, we can drop a perpendicular to our x-axis, always the x-axis. Now, this angle is not theta. This is our angle theta. But for the context of our problem, let's focus on this angle. And I will use sine distances. So this is 3, and this will be -3. The length of that side is not -3 units. That doesn't make sense. But it's a nice mnemonic device, a nice trick. So if we want to find the sine of theta, we can take B over R. And that's straight by the definition. Or you can think of it as, if we look at this angle, opposite over this length is essentially, or similar to, our hypotenuse, 3 square roots of 2. So we have B over r, which is 1 over the square root of 2, which is the square root of 2 over 2. Now let's look at cosine of theta. Cosine of theta is a over r. So a is negative 3 over r. Or you can look at this angle, and we can go adjacent, which is our negative 3. Now again, that's not really a side. That's not the length of a side, that is. But it can feel like that's adjacent over hypotenuse. So we have a over r, which is likewise in this case negative root 2 over 2. So you'll notice in this situation our trig functions can yield negative numbers as well as positive numbers, which is a twist compared to what we had in our previous understanding. Now tangent of theta is b over a. So b over a will be 3 over negative 3, or we can feel like opposite over adjacent. So we have 3 over negative 3, which is simply negative 1. Now, you'll notice that this feels similar to what we had in a 45, 45, 90 right triangle, or with our angle pi over 4. But there is a variation with our signed numbers, negatives, being presented. Now, we also need to find the next 3, but that's easy because we can just do the reciprocal. So, cosecant of theta. So cosecant of theta, I'll take the reciprocal of root 2 over 2, but the reciprocal of root 2 over 2, I'm going to have to deal with rationalizing the denominator. Let me take a step back and actually look at 1 over root 2 and just find the reciprocal of that. So we obtain square root of 2 over 1, which is just the square root of 2. Secant of theta will be likewise negative root 2 over 2. And finally, cotangent of theta will be the reciprocal of negative 1, which is negative 1. Let's look at another angle. Here we have a point on the terminal side being 8, negative 15. So let's sketch our angle. 8, negative 15 would be in the fourth quadrant. So again, we don't have to be incredibly exact. So let's go ahead and find r now. R equals the square root of 8 squared plus negative 15 quantity squared, which is 17. You may remember your Pythagorean triples from geometry class. If so, then that goes a little bit more quickly. Just be careful you don't make a mistake or you recall incorrectly. So here we have 8. Here we have negative 15, and our length of this line segment, which is akin to a hypotenuse, will be 17. So sine of theta equals b over r. So negative 15 over 17 will be negative 15 17ths, which does feel like, if I look at my angle, or something like my angle here, this is obviously not theta. Theta is this angle, but if I reference this angle, then opposite over hypotenuse, and using a signed distance for the opposite. Now we continue. Cosine of theta will be A over R. Tangent of theta will be B over A. So we have negative 15/8. And then, again, to find the remaining 3, we can take the reciprocal. Cosecant of theta is negative 17/15. Secant of theta is 17/8. And cotangent of theta is negative 8/15. So now we've seen that our trigonometric functions can take a different sign depending upon where they are. And by sign, I mean whether it's positive or negative. So we've seen where sine of theta could be negative, or cosine of theta could be negative, and all throughout. So that sign, positive or negative, is dependent upon where the terminal side lands. So let's draw an initial side. And if we look at a terminal side, with a point AB on it, and we know that R is always positive, so sine of theta would be B over R, and B is positive, and R is positive, then we have in the first quadrant, sine of theta would be positive. Cosine of theta is A over R, and in the first quadrant, A would be positive, and R is always positive, so cosine of theta would be positive as well. Tangent of theta is going to be B over A, and in the first quadrant, we have all of those are positive. Now the reciprocal functions likewise maintain the sign, SIGN, of their reciprocal. So cosecant of theta and sine of theta have the same sign. Cosine of theta and secant of theta likewise have the same sign. Now let's imagine then we move our angle to the second quadrant. So in the second quadrant, notice that in the second quadrant, A is negative, B is positive. So sine of theta would be a positive value over R, which is always positive. So sine of theta would be positive in the second quadrant. Cosine of theta, well, that's A over R, and in the second quadrant, A is negative. So cosine of theta will be negative. Tangent of theta is B over A, or you can think of it as sine of theta over cosine of theta. And sine of theta over cosine of theta will be a positive divided by a negative, which is, this situation, a negative. Now if we move on down to the third quadrant, in the third quadrant, A is negative, B is negative, and of course R is always positive, so B over R would be a negative divided by a positive, which is negative. Cosine of theta is A over R. A is negative, R is positive. And tangent of theta is B over A, or you can think of it as sine of theta over cosine of theta, and we have a negative divided by a negative in either instance, and that yields a positive. Now if our angle lands in the fourth quadrant, we'll notice that sine of theta is again B over R, and in the fourth quadrant, B is negative and R is positive, so sine of theta will be negative. Cosine of theta is A over R, and A over R would be a positive divided by a positive, which is positive. And tangent of theta is going to be b over a, which is a negative divided by a positive, or you can think of it again as sine of theta over cosine of theta, which is a negative divided by a positive, which is negative. Now, there is a mnemonic device for this, as long as you remember that your reciprocal functions, cosecant of theta, secant of theta, and cotangent of theta, are the same sign, sign, as their reciprocals. Then you can remember this rule. All of these are positive in the first quadrant. So we have all, and then in the second quadrant, only sine of theta is positive. In the second quadrant, we have tangent of theta is positive, and in the fourth quadrant, we have only the cosine. So we can have a mnemonic device of all students take calculus, where quadrant 1, all of them are positive. In the second quadrant, sine of theta is positive. In the third quadrant, tangent of theta is positive. And in the fourth quadrant, cosine of theta is positive. So we can look at ASTC for all students take calculus, all sine of theta, tangent of theta, cosine of theta. And then remembering again that cosecant of theta and sine of theta have the same sign. Cosine of theta and secant of theta have the same sign, and tangent of theta and cotangent of theta have the same sign. In this example, we want to find the quadrant in which theta lies. So, let me draw a quick sketch of our coordinate plane. Now, we are told that sine of theta is negative, and we are told that cosine of theta is positive. So let's look first at where sine of theta is negative. In the first two quadrants, all students, all are positive, sine of theta is positive, and then in our third and fourth quadrants, sine of theta is negative. So sine of theta is negative means that we could have theta in quadrants 3 or 4. But because cosine of theta is positive, that's only true in the first quadrant, or all students take calculus. We could have it in the fourth quadrant. So therefore, we know that theta must satisfy both requirements, and so therefore, theta must be in quadrant 4. In this next example, we have been given cosine of alpha is negative 4/5, all while knowing that tangent of alpha is also positive, and we're supposed to evaluate the rest of the trigonometric functions for alpha. So let's first identify the quadrant in which alpha lies. So cosine of alpha is negative. So cosine of alpha is negative means that we're either in quadrants 2 or 3. But at the same time, we are told that tangent of alpha is positive. Tangent of alpha is positive in the first or third quadrants. So therefore, we know alpha must be in quadrant 3. Okay, so how will we find the remaining trigonometric functions? So we are only told that cosine of alpha is negative 4/5. Well, we have a Pythagorean identity that relates sine of alpha and cosine of alpha. Sine squared of alpha plus cosine squared of alpha is 1. So we know sine squared of alpha plus the square of negative 4/5 should equal 1. So sine squared of alpha plus 16/25 equals 1. So sine squared of alpha is 9/25. But now we must take the square root of both sides. So we have sine of alpha equals, and now what squares to give 9/25? Well, 3/5 or -3/5. Now this is where it becomes important to know what quadrant alpha is in. And since alpha is in quadrant 3, we know that sine of alpha is negative in the third quadrant. So it must be -3/5. Now we can use the rest of our trigonometric identities to find the remaining trig functions. So we have sine of alpha is -3/5. We have cosine of alpha is -4/5. And tangent of alpha is going to be sine of alpha over cosine of alpha. So that's -3/5 divided by -4/5, which is a +3/4. And then our reciprocal functions, cosecant of alpha would then be -5/3. Secant of alpha is -5/4. And cotangent of alpha is 4/3.